start. So good afternoon, everyone. Welcome to this last May edition of the NITheCS Colloquium. My name is Francesco Petroccione. I'm the interim director of NITheCS. And this afternoon, we are very happy to have with us Isabella Rammala. Yeah. Isabella is completing her PhD at Rhodes University, but she's based at the South African Radio Astronomy Observatory in Cape Town, and she's working on analyzing MeerKAT data. And today she will give us a very interesting talk on a very interesting image that she produced not so long ago. That was advertised in every scientific and not so scientific journal and so on and so forth. So Isabella, people are here to listen to your talk. Thank you very much for being with us this afternoon. You know how the game works. You just need to press the green button to share your screen, and you're welcome to do it now. And while you do that, I will remind the participants to please either use the Q&A facility also at the bottom of the Zoom screen, or during or after the talk, raise your hand. And I think today we want to start an experiment. And the experiment is that we will record the talk, but not the questions. Yeah. And why it is an experiment? Because sometimes we have the feeling that people are not so keen to ask questions if they are recorded. Yeah. So we will stop the recording at the end of the talk. So hoping that people start engaging more with the speaker and among themselves. So Isabella, thank you very much. We can see your slides. You're welcome to start. Thank you.
Thank you, Francesco. Hi, everybody. For those who don't know me, my name is Isabella Rammala, and I'm a PhD student at Rhodes University. And today I'll be presenting some of my work with the MeerKAT Galactic Center data that was published recently. So I'll be talking mostly, this talk will be focused mostly on the compact objects in that data and some of the interesting sources that we have found. And later, eventually, I will present the catalog, an example of the catalog that we have that will eventually be published soon. So this talk was motivated recently by the inaugural image of the MeerKAT Galactic Center data. So we were sitting with my supervisors and we were just fascinated by this image. And then there was discussions going back and forth. And eventually they asked, looking at this image, we can see that there are so many sources. Sorry, let me just, I'm having difficulty seeing what I'm looking at with this. So I'm gonna move. Yeah, okay. So we saw that there are many sources in this complex region. This is the image of the Galactic Center, imaged at 1.2 GHz with the MeerKAT Galactic, with the MeerKAT L-Band receiver. And this is the original inaugural image. And on it, I am identifying some of the interesting sources that are currently known. There is at the center, SEG A, which is thought to be the dynamical center of the galaxy, where we have the supermassive black hole, SEG A star, that was recently imaged with the EHD telescope. Alongside that, on the left, we have the Sagittarius B complex, which is thought to be a molecular cloud with Sagittarius B2 being a region of currently young massive star formation in that region. And there's also a cluster, a couple of clusters of massive stars in there. I am showing here the quadruplet cluster, and alongside this area, there is another cluster, as well as in this area, cluster of massive stars. Along with that, there are some supernova remnants, Sagittarius D on the left of the image, and another supernova remnant on that bottom right corner, which is the end product of massive star explosions. With that, there is also these things called the non-thermal radiofilaments that are these magnetic tube-like structure, thread-like structures in the galactic center that have been a mystery in terms of what causes them. So the radio arc on the center of the image, the snake on the right, and the several NFTs that I have labeled are the new non-thermal radiofilaments that have been observed in this region. So looking at this image, we were wondering, there are also some compact objects, point-like sources at the background of this image that most probably would be background AGN or background extragalactic sources. So then when we're looking at this image, we're wondering, which of these galactic center compact sources are new sources, and how many of these could be possible galactic center pulsar candidates? And so this talk will be mostly focused on these two objectives. It would be focused on how we classify these compact objects, where I'll talk a little bit about how we image, we produce the higher resolution images, how we identify the sources of interest, and how we group them into classes. And the second part of the talk will be focused on identifying the possible pulsar candidates, which will focus mainly on the classification criteria of these compact objects, and using their morphological structure, the environment, and the spectral properties of these sources to identify sources of interest. So for those that are not aware, you may be wondering, why would we want to look for pulsars in the galactic center? So pulsars in the vicinity, or radio pulsars in the vicinity of a massive object like a supermassive black hole, such a star, can be used as tools to study the structure of the interstellar medium in the galactic center. So we know that the interstellar medium is supposed to be magnetized and ionized, and we can use pulsars because they are sources that can be accurately timed, and we can use these time of arrival to study or infer the magnetic properties or properties of the interstellar medium through which they propagate. We can use them to study the magnetic fields of the galaxy. These sources can also be used in the vicinity of the J star to test theories of gravity. And also, there was also recent observations of an excess of gamma rays in the galactic center. And there are a few theories of what might be causing this excess gamma ray, some of which propose dark matter as a source. And other theories suggest that millisecond pulses may be, or undiscovered millisecond pulses may be the source of these gamma rays. So if we find millisecond pulses, or the lack thereof, may kind of add on to those theories. So to understand why we expect pulsars in the galactic center, we first need to know how pulsars are formed. So pulsars are formed when a cloud of molecular gas collapse on itself and form larger stars. And as the stars evolve and they become red giants, I'm referring to the bottom of the figure there. As they evolve and become red giants, or what we call massive stars, at the end of their nuclear fusion, they eventually explode into supernova explosion. And whatever remains is a very dense neutron star or a black hole if they are massive enough. And if the end product of the supernova is a neutron star, and that neutron star has highly magnetized beam of radio emission that are pointed in our line of sight, with every rotation as the beam sweeps in our line of sight, we detect a pulse of emission, and we call that neutron star a pulsar. So these stars are, or these pulsars are very stable clocks that when we can accurately model them, we can accurately, very precisely predict at what time is the next pulse going to arrive on Earth. And therefore they are what we call galactic clocks sometimes. And in the galactic center, currently, there are only 5 pulsars. So here on this figure, I'm showing the zoomed in version of the galactic center image. And that bright region here is where the dynamical center, the black hole, Sagittarius A star would be. And closer to that, we have a magnetar. And at the outskirts of it, about within 1 square degree, we have only 5 known pulsars plus that magnetar. When we look at the properties of these pulsars, they have what we call a high dispersion measure, which determines the amount of electrons that they go through in the galactic center before they arrive on Earth. So then, where are all these pulsars that in the galactic center that we expect? The reason why we would expect pulsars in this region I haven't mentioned is that this region has clusters of massive stars, which are progenitors to the pulsars. But then when we look for these pulsars, we're not finding them. So what might be the cost for that? There are few suggestions. One is that perhaps the way that we are searching for pulsars is limiting us when we have to search for pulsars in the galactic center. And the way that we traditionally search for pulsars is that we would take a telescope, do a blind survey of a desired area in the sky, and then we do a blind search. We collect a long time series of data, and then we Fourier transform this time series to search for periodic or harmonics from the periodic signals. So the way that we do is that for each radio, for each channel, we would collect a channel in the band of the telescope. We would collect time series data, and then we would have an estimate of a dispersion measure, which determines the time of arrival of the pulsar. That depends on the frequency. So the time of arrival is directly proportional to the frequency to the -2. And the dispersion measure is the constant, proportionality constant. And it depends on the amount of electrons that the pulsar or the signal travels between the location in the galactic center and on Earth. So obviously, in the galactic center region, they are it's a very complicated region of free electrons. There's a lot of free electrons in that region. Therefore, this dispersion measure will be high for pulsars in that region. And therefore, so traditionally they would do an estimate of the dispersion measure. So they would de-disperse or realign the pulsars with that dispersion measure and Fourier transform that to get the amplitude spectrum. And then they would save that as they would save a candidate. And if there is another dispersion measure that they would go through the cycle for a number of dispersion measure. And therefore they will, at the end, they will, when there is no other dispersion measure, they will fold the candidates with the best dispersion measure and they will get a pulse. However, the problem with this method is that, like I mentioned, the galactic center has a whole lot of electrons, free electrons, and this causes scattering in this region. So as the light travels from a pulsar, it traverses through this dense ionized medium, and this inhomogeneous medium will scatter light in and out of the line of sight, causing what would have been a very broad, narrow pulse as it arrived on our telescope to be a broader pulse. And the scattering is actually, the scattering time is directly proportional to frequency -4. So this means that as we go to a lower frequency, the pulse that we are detecting is now more broadened. And therefore, this scattering can render any or all periodicity searches at low frequencies impractical. And therefore, someone might say that maybe because this, as you can see at the bottom there, I'm showing an example of the pulses that are being recorded for this pulsar, J0, also 0742 - 2822. At the lower frequency, you can see that at this frequency, the pulse is completely scattered out. So therefore, if you were to do that dispersion measure Fourier transform, you will not detect any periodicity in that frequency. But then as you go to a higher frequency, you can see that now the pulse is coming out. So therefore, someone might say that then why don't you just search at a higher frequency where scattering is less pronounced? Which brings us to the second problem, is the spectral behavior of pulsars. Pulsars are very weak radio sources, especially at high frequencies. They follow a power law where the flux of the pulse is dependent on the frequency, the alpha, where alpha is the spectral index of the pulsar. And the spectral indices for pulsars are mostly steep negative. So that means if you were to observe a pulsar that's very bright at low frequency, it would be, you might not see it at a high frequency. So we have these two problems where at low frequency, you observe a pulsar and you might not see it if it's traveling through a high medium where it's the free electrons are scattering out the pulse. And then if you're observing at a higher frequency, you may not see the pulsar because, again, at the higher frequency, the pulsar is very weak. But then the observation of the magnetar in the galactic center, which I'm showing here, just an approximation, closer to Sagittarius A star is the magnetar J1745-2900. This is a highly magnetized neutron star that's been observed in that region. And so given the fact that we could observe the magnetar, this is motivation enough for us to continue looking for ways to search for pulsars in that region. So the proposed alternative method of searching for pulsars was to use image synthesis. So there was a suggestion by Codus and Lesio 1997, where they suggested that perhaps we can identify pulsar candidates in images and use the candidates' properties to go search for the pulse emission in the time domain. So we followed this method, and the advantage of this method is that you will be able to identify the morphological nature of the environment, and along with if you're able to see the pulsar in the image, you can get the spectral properties of the source, and using that spectral properties, using the morphological nature and the spectral property, you can distinguish the pulsar candidates from other compact objects that may be having similar properties from pulsars, such as steep negative extragalactic objects. And in addition to these, it is advantageous to search in continuum because continuum data is obtained from interferometers, and traditionally pulsars were searched using single dishes. And with interferometers, we have beams that are much larger than with single dishes, and therefore we can cover a large area of the sky at a time. However, there are also disadvantages to using continuum data to search for pulsar, because pulsars are very weak radio sources, as I've said, and they have short duty cycles. And therefore, when we integrate the data to synthesize the image may contain more noise than it would the emission from the pulsar itself. And therefore, there's a chance that if there is we might not see weaker sources in this method, but it's a start. So what we would plan to do with this data was to identify pulsar candidates in the continuum data with properties that are similar to pulsars. So this would be the spectral index. So we would we'll classify the compact objects, and based on their environments and their spectral properties, we would select those that matches possible pulsars. And we would do this disregarding whether the emission is pulsed or not. And then we would use this catalog later on for intensive periodicity searches in the time domain. So to do this, we had to first re-image the data from the inauguration of MeerKAT. So the data that we had was raw MeerKAT data observed between May and July 2018 at L-Band. We had observed about 20 pointings, but eventually ended up using 16 for this study. So 16 pointings with covering the central region of the galactic center, with the target being J star. And in total, out of the 64 dishes of MeerKAT, we had on average between 60 and 62 for each observation. And the correlator was configured to deliver 4,096 spectral channels between 856 and 1.7 gigahertz, or 856 megahertz and 1.7 gigahertz. And we had an integration time of about 8 seconds, with each pointing observed for about 10 hours, giving a total of 215 hours telescope time. And so how we would, the observing strategy for this was that we would observe, where they observed 10 minutes on a target, the target point, the target source, and they would alternate this from the target to 80 seconds on the secondary calibrator. So this is a source that will be used to calibrate the data that is closer to the target itself, but not necessarily known with known, we don't really know the flux, or the flux is not really, it could be invariable. And then we would cycle between the target and the secondary source about 4 cycles. And then we would skip to a primary source that is observed for about 10 minutes. So the primary calibrator is a calibrator that is known properties, so known flux, that will be now used to calibrate the secondary source, and using those solutions to calibrate the target. So we will observe the target, the secondary 4 cycles, and then we would observe the primary, and then go back to another cycle, 4 cycles of the target on the secondary. So at the end, we would have, so here I'm just showing you the workflow on how we image the data. So for each pointing, we had the raw archive data from the MeerKAT archive, and we would convert this data from the raw data to what we call measurement sets, which is the format that's used by our radio imaging softwares. And then for each pointing, each measurement set would have a calibrator or calibrators, the primary and the secondary, and the target. And for each of those measurement sets, we would go through a flagging process where we are removing general galactic neutral hydrogen, cutting the bandpass edges, and removing any signal from telecommunication satellites. And once that's done, we would do, on the primary calibrator, we would do telescope delays, and we would do frequency bandpass calibration, and we would apply, we would also do the time-dependent gains on the secondary, and then we would apply that to the primary and the secondary calibrator, and then we would take the solutions and apply them to the primary and the secondary, and calibrate for the flux, and then we'll take those solutions to the target, and then we would split the corrected data into a target measurement set. And then from there, we would image the data using the software called WS Clean. So this is where we go and look or manually observe or look at the image and create a mask. And we apply the mask onto the image, and we do what we call a self-calibration, which is we used the software called Cubicle, and then we would re-image. And again, if we're not happy, we would create another mask and re-image. And once we're happy with how the image comes out, we would produce a high resolution image by changing the parameters on WS Clean. I think we set the bricks robust to -1, which produces high resolution images. And then from there, we would produce for all the pointings, or for all total intensity images of each pointing, we would produce a mosaic, and we would also sub-image the total intensity image for spectral index measurements that we later do. And this is what we end up with, which is a high resolution image of the galactic center. And this was presented in the recent paper by Haywood et al. 2022, where you can see most of the sources that I've shown in the original inaugural image. The radio arc, you see now more in details the radio filaments. There are more point sources in this on the outskirts of the images. There are supernova remnants. There's the mouse pulsar and star formation regions as well. So from here, we went on to, I spent quite a lot of time just zooming in this image, looking at what might be interesting. And some of the few interesting objects that we have observed was I'm only just showing you a few here. There was this source here that sort of has a tail, kind of reminded us of the mouse pulsar, which is the pulsar here that is a runaway pulsar from the supernova remnant. However, this is not really associated with any supernova remnant, but it's an interesting source. Also on the left here, there's another one that looks like might have a tail, and there are a few more in this region. And also there is a known pulsar that miraculously is visible in this image. So this is PSR J1746-28. This is a known pulsar that we can now see with the MeerKAT in continuum data. So then we went on to classify most of these new sources. So for me to be able to do this, I had to first label known sources in this region. So I know where the known things are and where to look for unknown sources. And I found this master radio catalog, the HAIRSEC master in the NASA HAIRSEC master radio catalog. So it has, it's a catalog of all known radio sources at different observing frequencies. So after going through this huge catalog, I think about 20, if not more, catalog had sources that were in our region. So here I'm just showing you the catalogs that have sources within our region and the number of known sources. So majority of known sources in this region are the NVSS and the SRGA, REGSCSC. by Yusuf et al. So this is mostly filament sources, non-thermal filament sources. So the first strategy we tried was to obviously use automatic source finders to identify any sources that are in this region. But this region is very, very complex and has a whole lot of sources. And our source of interest are mainly compact sources, and Sagittarius A star is a very bright source. So the emission from Sag A star are corrupting, or they extend outside of this region, and therefore it's difficult for a source finder to pick out small or point-like sources in this region. So when we were using source finders, we quickly realized that that's not going to be the best method for us to use. So eventually it reverted to having to use manual extraction. So this meant that I had to manually go through this image and identify all new sources that are in this image. So the first step that I did was to divide the image into, so tiling up the image into small tiles, so that I don't lose my mind. So then I'll be able to search one area at a time. And then I also labeled known sources. So each tile would have known sources that are, if any, they will be labeled. And therefore there will be other sources that I would have to go now identify by hand. And so I went through this tiles or sub images, and I've also went on the outskirts of the image and ran a source finder. So for regions outside of, or at the edges of the mosaic, I was able to run a source finder, firstly, because I needed to confirm that some of the sources that I find by hand in this region are found by a source finder. We could do this because at the edges of the mosaic, emission from Sag A star is not that much. So we are able to pick out, or this complex emission is not that much. So we're able to pick out point sources. So in this image here, I'm showing you sources that we found. The yellow color indicates known radio sources. Magenta is all the sources that have been identified by hand. And then the red points are sources that were identified with a source finder. So after that, validating our method of that we find sources with an source using a source finder, in total, we had about 1,500 or so new sources in this region. And therefore we had to go through and classify these sources. So they were point sources. So we had, I think, about 7 classes. So point or compact sources were any source that has a very, that is point-like. So I'm showing you 4 examples of unresolved point-like sources with a few arc seconds angular size. So those would be all of those sources that are identified as point sources would go into this class. And then we also had sources that look AGN-like. So these are extragalactic source-like. Any source that had a bright center and 2 brighter region like AGN-like or if it has a bright source and jets coming out like source. So we would put that in the AGN category. And then we also had these shells, shell-like sources. So these would be ring-like with a hollow area. So could maybe potentially be so these were shell-like sources that could potentially be planetary nebulae or other sources. So anything that was ring-like, we put it in a shell category. And then we had all these other sources that looked kind of like cloudy, clumpy, that we called a cloud source. So we have another category called cloud that contains these. And then we have these tail-like sources. This is mostly motivated by the mouse pulsar. So any compact or unresolved point-like source that has some sort of a tail, we noted, disregarding the fact that some of them could potentially be one-sided AGNs, but we just noted them into the tail category until we get their properties. And then we also identified point sources that are associated with these filamentary structures for the non-thermal filaments catalog. So any filamentary type source that has a point source with it, we identified in this category as well. And in the end, we ended up with a full catalog of sources. They are positioned, they are flux, and they are spectral indices, which I thought I would not have time to talk about in this talk. And but we also measured their spectral indices and their category or the class that we identified. So we have a full catalog of these sources that will soon be published. So if you have any interest in any of these sources, look out for that publication. And yeah, so this brings me to the end of my talk. If you have any questions or any suggestions, please do ask. Thank you.
Yeah, Isabella, thank you very much. It was a fascinating talk. Thank you very much. And it sounded like lots of work. So well done. Well done. Well done.
Thank you.